During the last lecture, I promised to prove why certain rings were examples of unique factorization domains, and in particular why PIDs are UFDs. Let me remind you the definition. A principal ideal domain it is called a PID for short, and it is a very common name. A principal ideal domain is a domain where every ideal is principal. That is generated by one element. Easy examples are fields and Z, and also if F is a field, then the ring of polynomials is a principal ideal domain. And like I did during the last lecture, I would like to postpone the proof of this example for later in the lecture. On the contrary, polynomials with integer coefficients do not form a principal ideal domain because the ideal generated by elements x and 2 is not principal. It cannot be, so elements x and 2 cannot be divided by one common element. And starting the proof that a PID is a unique factorization domain, one proposition is that every irreducible element of a principal ideal domain R is prime. For the proof, assume that P in R is an irreducible element, and consider the ideal generated by P inside R. So we want to prove that this ideal is prime. We want to show that P is a prime ideal. By our definition during the last lecture, an element P is prime if and only if the ideal that it generates is prime as well. So let us check primeness of this ideal by taking elements A and B in R such that A times B belongs to the ideal, which means that A times B is C times P for some element C in R. Then consider a bigger ideal generated by two elements B and P, and recall that R is a principal ideal domain. So by definition, this ideal is also generated by one element. Let's say that this element is Q. For some Q in R. And so the ideal generated by P is a subset of the ideal generated by Q. And this inclusion means that P is a multiple of Q, such that P is D times Q. But note that P is an irreducible element. We started with an irreducible element P, which means that either D is a unit or Q is a unit. Let us work out both cases separately. In the first case, if D is a unit, then it means that the ideal generated by P which is by this equality the same as ideal generated by dq, should be equal to the ideal generated by q, because here we just multiply q by an invertible element, and this does not change the ideal. But then recall that q generates the ideal formed by elements b and p. And so we have the equality of two ideals. So b should belong to p. And in this case, we proved that one of the elements, one of the factors belongs to P. And in this case, we proved that P is prime. P satisfies the definition of a prime ideal. So let me write P is prime in this case. Let us consider the second case where Q is a unit. Since Q is a unit, it generates the unit ideal. So B, comma P, which is the ideal Q. It coincides with the unit ideal R. And now we can consider all the elements of these ideals multiplied by A. So we multiply all the elements of this ideal by A. And we get the ideal generated by AB and AP. But AB is equal to P. AB was in the ideal P. So we have that this is contained inside the ideal generated by P. On the other hand, we have that B comma P is equal to R. So this product is formed by taking every element of R and multiplying it by A. And this is the same as considering the principal ideal generated by A. And so by following this sequence of equalities and noticing this inclusion, we observe that A lies inside the ideal generated by P. And so the element A itself belongs to the ideal P. And so we prove that one of the factors is in the ideal P. So we prove that with this assumption, P satisfies the definition of a prime ideal. So P is prime, satisfies this definition in this case too. And so we considered both cases and showed that either A or B belong to P to start with, and therefore we can conclude that P is a prime ideal. So P is a prime ideal, and this is equivalent to saying that P is a prime element. And so we prove that every irreducible element of a PID is prime. Now we have one of the ingredients to prove that every principal ideal domain is a unique factorization domain. So second proposition of this lecture: if R is a principal ideal domain, then it is a unique factorization domain. For the first step in the proof, I would like to remind you that a unique factorization domain is a domain where factoring terminates and is unique. And we showed last lecture that factoring terminates if and only if every ascending chain of principal ideals stabilizes. And we also proved during the last lecture that in the presence of factoring, uniqueness of factoring is equivalent to saying that every irreducible element is prime. So you can probably see the idea of the proof now. We proved that every irreducible element is prime in the previous proposition, and so we want to prove that factoring terminates. And for this, it will be easier for us to operate with chains of principal ideals. So the first step, we take an ascending chain of principal ideals. So we have A1 is contained in A2, is contained in A3, etc. Then I want to note that if we have any ascending chain of ideals, I1 is contained in I2, is contained in I3, etc. Then their union, which I call J, is the union of In, n starts with 1. It is also an ideal. So check additivity. If we have I1 and I2 in IN1 and IN2 respectively, then one of N1 and N2 is bigger. So let's say that N2 is bigger than or equal than N1. Then both I1 and I2 are in this IN2. And since IN2 is an ideal, the sum of these elements also belongs to IN2. And therefore it belongs to the union. And so J is closed under addition of elements. And for multiplication, if we have I inside of J, then I lies in some IN. We can represent I in some finite step of the union. And then for any R times I belongs to IN by the definition of ideal for IN, and therefore it belongs to J2. So J, belongs to the union of IK, K starting from 1, which is J. And so we proved that J is an ideal. And so from this note, we say that the union of ANs, and starting from 1, is an ideal. In R, but R is a principal ideal domain, so there exists an element B inside of R which generates this ideal. Now let us study this ideal and this element B. B belongs to this ideal, so it belongs to the union and starting from 1 AN. And so there exists a finite step, AK, such that B belongs to the ideal generated by AK. But this means that we have just proved the inclusion that B is contained inside of AK. And we know from the first step that AK lies in the union of ANs, which is B. And since we have two reverse inclusions of two sets, it means that these two subsets of R coincide. So B is equal to AK. And since all the further steps, AK plus 1, AK plus 2, etc., are first contain AK and second are contained in B, it means that they all must coincide too. And this is the proof that this chain of principal ideals stabilizes. And this proves that factoring of elements terminates in a principal ideal domain. And for the third step, since we know the fact about factoring, we show that factoring is unique by recalling from the previous lightboard that every irreducible element in R is prime. And then from the results of the previous lecture, it means that factoring is unique. So R is a unique factorization domain. I have already told you several lectures ago how to see that Z is a principal ideal domain. And let me briefly remind you. I took an ideal I in Z, and to show that it is principal, I would take the smallest positive integer in I. So I used the notion of smallest, so we have some sort of size function to compare integers. And let's say that this integer is n, and I want to say that this integer generates the ideal I. So let's take some other element of I, x in I, then I can divide x by n with remainder, so we have x is equal to n times some integer q plus remainder with the absolute value of the remainder strictly smaller than m. And I said that since x is in the ideal and n is in the ideal, then R should also be in the ideal, being x minus nq. But since the absolute value of R is smaller than the absolute value of n, which is the smallest possible absolute value of an element in I, it means that R must be equal to 0. And so for this proof, I used the notion of smallest, so some size function on the ring Z, and I used the division with remainder to show that every element of I is divisible by n. And so now I would like to abstract this idea of division with remainder. And for a domain R, I define a Euclidean function to be this entity, a function n from R without the zero element to non-negative integers. Such that if we have an element A in R and an element B in R without zero, then we can divide A by B with some remainder. So then there exists a quotient Q and a remainder R in R, such that A is equal to BQ plus R. So A is equal to BQ plus R, and either R is equal to 0, so B divides A, or the size of R is strictly smaller than the size of B. And we say that R is a Euclidean domain if it possesses at least one Euclidean function. And the reason why we call it a Euclidean function and a Euclidean domain is because this function allows us to run a Euclidean algorithm. The most important fact about division with remainder is that B divides A if and only if R is 0. Some examples. Example Z with n of an integer A being the absolute value of A. Then f of x, the ring of polynomials where f is a field. This is also a Euclidean domain. With a Euclidean function n of A of x defined as the degree of A of x. And we divide with remainder by using long division of polynomials. So, for example, I want to take f2 of x, and I take polynomial a of x is equal to x cubed plus x squared plus x, and I want to divide it by the polynomial b of x, which is x plus 1. Then I run the long division algorithm. I have x cubed plus x squared plus x divided by x plus 1. And then I kill the first summand by writing x squared. So x squared times x plus 1 is equal to x cubed plus x squared. So here we get 0 plus x. And now by taking x plus 1 times 1, we can kill x. So this minus this, we get 1. And I just want to remind you that minus 1 is equal to 1 in f2. And so a of x is equal to b times x squared plus 1 with the remainder 1. So in this case, q is equal to x squared plus 1, and r is equal to 1, and the degree of r, which is 0, is smaller than the degree of b, which is 1. And now I want to finally follow up with my promise of showing that the ring of polynomials with coefficients and fields is a unique factorization domain by showing that a Euclidean domain is a principal ideal domain. And for the proof, I'm going to recreate the analogous proof for integers. So let us take R, a Euclidean domain, and let us take an ideal I in R. And we know that there is a Euclidean function from r minus 0 to non-negative integers. So in I minus 0, pick an element R with the smallest possible n of r as evaluated on non-zero elements of this ideal. And there may be several such elements. For example, for integers, we could take the negative counterpart of the integer that we took in the beginning, but it's not a problem. We can show anyway that R generates the ideal I. So we take an arbitrary element I of I, and since we have a Euclidean function, we can divide with remainder. Oh, I think I picked a wrong letter R. I will replace it with the B. So we want to show that and divide by b. So I is equal to b times q plus r. And r is the remainder. So if n of r, if r is non-zero, so if b does not divide I, then n of r is strictly smaller than n of b. But this contradicts our assumption that b has the smallest norm. So r is equal to 0, and so for any I, for any I in the ideal I, b divides I. And it means that the element b generates our ideal. And so we prove that I is a principal ideal, and it means that R is a principal ideal domain. In particular, a Euclidean domain is a unique factorization domain, because a principal ideal domain is